So now we'll go through a couple of my MATLAB examples having to do with rational functions. And again, there's a lot of information here to take in. All right, in question one, we're asked to find the domain of the rational function. In order to find the domain, all we have to worry about is when our denominator could possibly be equal to 0. Because if it's equal to 0, we get an undefined fraction and we don't have a function value. So the technique that we use is you take the denominator and find its root, set it equal to 0. You solve for x using opposite operations, and I find out that the denominator will equal 0 when x is equal to -20. So this is the value that I do not want to include in my domain. So if you look at the choices here, choice A says the domain of R of x is, and it has set builder notation here. The only part you need to fill in is the -20. If we were asked to do this in interval notation, you would want to consider what numbers you're trying to describe. So here's a number line, and the number 20 is no good, but everything to this side and to this side is okay. So to write this in interval notation, if we needed to, you would begin by saying this is -infinity out here, up to the number -20. Put a round bracket there because we can't equal -20. And then write the interval for the right-hand side, from -20 to +infinity. Now, number 2 asks us to do the same thing, but we've got a more complicated denominator here. So in this particular case, we're once again going to find the root for the denominator. So I'm going to set it equal to 0. Now in this case, you can just do the opposite operations, getting rid of your addition first, and then getting rid of the square on the x by taking the square root. Now, in an earlier video, we talked about when you introduce the square root symbol, you need to consider that there are, in fact, 2 roots. A positive root, in this case, square root of 9 can be 3. There's also a negative root. It could be -3, because both of those numbers, if you square them, will give you 9. So we have 2 values that we do not want in our domain because they will cause the denominator to equal 0. So you can see the directions here say use a comma to separate answers if needed. So this is how you would put your answer in. And to write this one in interval notation, if you have to, it's a little more complicated. I've put open circles at the values of -3 and +3 to show that for this rational function, we cannot equal those values. But everything in between is okay to substitute into the function. Everything to the left of -3 and everything to the right of +3 also does not create a problem. So you can see that in order to write this in interval notation, we actually have 3 sections to describe. The first section is from -infinity up to -3, round bracket, union, -3 to 3, union, and the last section is from 3 and up, 3 to infinity. That's how you would write this one in interval notation. I want to go back to the second problem for just a minute because there's something that we should take the opportunity to review. This denominator is a quadratic equation, and when it's a quadratic equation, and you set it equal to 0 in order to find the roots, in this case, because it's a simple binomial, we can just move the 9 and then take the square root. However, you should be aware of the fact that we can factor this. And this is another factoring method that we didn't discuss in our previous videos. We talked a little bit about GCF. We talked a little bit about A&M. This is known as difference of 2 perfect squares. When I talk about perfect squares, the perfect squares are the numbers that result from squaring a basic counting number. So if I take 1 and square it, I get 1. 2 squared is 4. 3 squared is 9, 4 squared is 16, and so forth. And in this particular case, I have a perfect square here, 9, after the subtraction sign. X squared is called a perfect square because it's x times x. And I have subtraction, which is the difference of two perfect squares. Has to be subtraction here for this method of factoring. When you face difference of two perfect squares, you will always get two binomials. You split up the first term into equal factors, x and x, when multiplied give you x squared. And then you split up the second term into equal factors of 3 and 3. I don't want to use 1 and 9. They have to be equal for this method. And in order to get a minus 9, one of these has to be positive and one would have to be negative. And that's the correct factored form. And like in a previous video, if you take each factor, set it equal to 0, you can see that we do get those two values we want to exclude from our domain. And let's take a look at just one more example of that factoring. So suppose my function looked like this. And on the bottom, maybe I have x squared minus 36. Okay, as before, we take a look at our denominator and we know we want to set it equal to 0. This is again difference of two perfect squares because x squared is a square. It's x times x. 36 is a square because it's 6 times 6. So I set up my two binomials, split up the first term into equal factors, x and x, split up the second term into 6 and 6, always 1 plus, always 1 minus, and from there I get my two values I would exclude from the domain. So again, just to stress, when you write that domain, remember you don't want to equal these values. Now there's one other situation we should take a look at, and that is sometimes they do you a little bit of a favor. And when they give you your rational function, it's actually already factored. So you might see something that looks like this. When you see it already in sets of parentheses multiplying each other, this has been factored. Now, when you want to analyze your domain, you look at the denominator only, you set it equal to 0, and because it's already factored, all you have to do is now split those factors apart, set them equal to 0, and solve. So it's as if someone did the work for you because they have put it into a factored form. All right, so hopefully that's helpful. Now let's go back. For our third example, we're asked to find the vertical asymptotes. But just for practice, I'm going to go ahead and try to find the domain for this one as well. My denominator is x squared plus 12, and I would set that equal to 0. Now this is not one I can factor by difference of two perfect squares. First of all, it's addition. It has to be subtraction. And second of all, 12 is not a perfect square number. So my only option here is to just clear things away from the x. Now I get x squared equals negative 12. When I introduce the square root on both sides, I run into an issue because I'm told that x should equal the square root of a negative number, which is imaginary. So what this is telling me is there are no real values that I need to exclude from domain. And that would mean that my domain would be everything from negative infinity to positive infinity. Now again, the question didn't ask for that, but again, it's just good practice. All right, now to find the vertical asymptotes, you set the denominator equal to 0. So in the process of finding your domain, you've actually done the work you need to do to find your vertical asymptotes. Now, since my equation was not solvable, I don't have any vertical asymptotes. And in addition to the fact that I don't have any vertical asymptotes, I also don't have any holes in the graph. Remember, holes in the graph come from common factors in the numerator and denominator. I can't factor either the numerator or the denominator, so therefore the correct answer for this one will be D. There are no discontinuities here. All right, that last example really wasn't typical, so let's look at a more typical example. Find the vertical asymptotes, if any, and the value of x corresponding to wholes for this rational function. Now again, for the practice, I'm going to go ahead and start right with the domain. And again, domain means take a look at your denominator, set it equal to 0, and see if there's going to be problems. I'm going to, again, just to practice the factoring, push factoring here. This is difference of two perfect squares. It's subtraction, x is a square, and 25 is a square. It's 5 squared. And solve. And I have discovered that there are two times when the denominator would be 0, and that's if x is positive 5 or negative 5. So for my domain, these are the values I would want to exclude. When you're trying to find the vertical asymptote, you do similar work, except when you're looking at vertical asymptotes, you need to consider the numerator. So I'm going to keep x minus 5 in the numerator, and you will write your denominator in a factored form. And the reason it's important to have both the numerator and denominator is I need to see if I have common factors. In this case, I have an x minus 5 in the numerator, and I have an x minus 5 in the denominator. This is an example of having a common factor. Anytime you have a common factor, the root that you get when you set that factor equal to 0 and solve is always where a whole is located, a point of discontinuity. At x equals 5, I will have a hole in the graph. Take any remaining factors in the denominator, set them equal to 0 and solve, and that gives you the equation of the vertical asymptote. So if we go back and look at our choices for this question, we do have a vertical asymptote, and we have a hole in the graph. So the correct choice would be B. My vertical asymptote is at x equals negative 5, and there's a hole at x equal positive 5. The last thing you need to be able to find for a rational function is the horizontal asymptote if there is one. And again, if there is one, there will only be one. So for horizontal asymptotes, there are those three rules. And the three rules, remember, depend on the degree of the numerator and the degree of the denominator. So the degree of my numerator, I go to the variable x, and there's only one x, so it's automatically the highest. And if there is no exponent, it's always a 1. So the numerator has a degree of 1. The denominator, the highest exponent on an x, is a 2. So that gives me a degree of 2. So in this case, my degree of my numerator is less than my degree of the denominator. The horizontal asymptote is always the x-axis, which has an equation of y equals 0. Here's another example. Again, I'm asked to find the horizontal asymptote. My degree of my numerator, highest power of x that I see, is 2. My degree of the denominator, highest exponent I see, is 2. When the degree of your numerator is equal to the degree of your denominator, which is what I've got going on here, there is a horizontal asymptote. Because it's a horizontal line, it begins y equals, and you make a fraction out of the leading coefficients, the coefficients on those terms with the highest power. I have 12 as my leading coefficient of my numerator. Denominator has a leading coefficient of 3, and I certainly can reduce that to be y equals 4. So that would be my answer. Okay, but you can see how it all comes down to knowing your rules. This example, I'm going to preview it right in my math lab because there's an interactive figure that you need to use. It says use the A, B, and C sliders to graph this rational function. Now this has got a rational function and it's got a shift applied to it. So I'm going to click to get to the interactive figure. So you can see my equation is supposed to be 3 over x plus 2 plus 1. Compare your equation to the one at the top of the interactive activity. You can see a is supposed to be the numerator. For my function, a is 3. So I want to move my slider until I get to the value of 3. Now my b value, if you look, b is in the denominator attached to the x. My denominator is positive 2, so I will move that slider to positive 2. And my c value, my constant at the end, is positive 1 for my function. So going back to the question, the first thing we're asked is for the domain. Well, this time we've got the graph to work from, which is very helpful. And in the interactive environment, you have a domain checkbox. You can see that what they did is indicated that the domain should include everything headed out to negative infinity until you get to negative 2, round bracket. And then you pick up on the other side of negative 2, round bracket, to positive infinity. So over here, when I have to do this in interval notation, I'm going to do negative infinity, use the palette down below, to negative 2, to positive infinity. Good job. What's the equation of the vertical asymptote? Again, going back to the interactive environment, I can hit this checkbox to put in the asymptotes. And you can see it's labeled x equals negative 2. So that's my vertical asymptote. Rocking it. For part 3, what's the equation of the horizontal asymptote? So if I go back to the interactive environment, I can see that my horizontal asymptote is y equals 1. So just a little practice reading graphs. All right, this last question that I'm going to demo does a nice job of kind of summarizing everything. It says, follow the 7-step strategy to graph the following rational function. First, determine the symmetry of the graph of f. Is it going to be y-axis, origin, or neither? This is a good review of even and odd functions. I would need to substitute a negative x everywhere I see an x in the original function. Then I simplify. And in the denominator, what happens when you square a negative number? Well, a negative x times a negative x would be a positive x squared. And at this point, I would stop and compare this to my original function. And since it is the case that f of negative x is the same as the original f of x, this function is even. Even functions have y-axis symmetry. Remember, if f of negative x had turned out to be equal to negative f of x, if they had the opposite signs, that would mean the function is odd. What's the y-intercept? In order to find a y-intercept, you always allow the x coordinate to equal 0. I'm going to replace the f of x by a y. I would have y equals negative 1 over 0 squared minus 4. That's the same as y equals negative 1 over minus 4. A negative divided by a negative is the same as a positive number. The y-intercept is 1/4. What is or are the x-intercepts? To find the x-intercepts, I'm going to let y equals 0. So I put 0 on the left of my equation. Now I have to solve for x here, which might send you into a little bit of a panic. But you can make your life a lot easier when you have a fraction on one side to get a fraction on the other side of your equation, which can be done by putting any number over 1. Now I'm able to cross multiply. And when you cross multiply, you multiply along the diagonals in one direction. 0 times anything in the universe is going to be 0. And then I go back and multiply the other direction, putting an equal sign in between my two results. 1 times negative 1 is negative 1. I get a nonsensical statement, and that's telling me there is no x-intercept. In order to find the vertical asymptote, I'm going to take my denominator, set it equal to 0, and solve. Split the x and x. 4 gets split into 2 and 2. Now, because this is the vertical asymptote I'm finding, I want to pay careful attention and make sure I don't have a common factor in my numerator and denominator. And I'm able to factor the bottom into x plus 2, x minus 2. Do I have a common factor? No, because neither of these factors in the bottom is the same as a factor in the numerator. Therefore, these are my equations for my vertical asymptotes. My horizontal asymptote. Okay, this is where I need to know the degree of my numerator and the degree of my denominator. Degree of denominator is no big deal. I can see the highest power of x is 2. Degree of the numerator, however, is kind of a challenge because I don't have any x's. When you don't have any x's there, that's the same as saying this is -1 with an x to the 0 next to it. So a little recap, anything to the 0 power is 1. 1 times -1 would keep my numerator -1. So this is an equivalent way to write the numerator where I haven't changed its value. The degree of my numerator is 0. My numerator is less than my denominator. So I do have a horizontal asymptote. Consulting the rules, I know it's y equals 0. And the last thing they want you to do is they've given you some values. You want to look at this like it's a table. So in the first spot, I'm supposed to plug -7 into this fraction. I'll go off and do that off to the side. My numerator is going to stay the same, keep the minus sign in front. I have -7 squared is +49. Take away 4 is 45. And there's no reason to get a decimal for that. That fraction is as reduced as it's going to get. So that would be my answer for the first blank. You would continue doing this all the way through the table. And now we're ready to decide which of these graphs would be the correct graph of this function. In each case, you can see they have the same vertical asymptotes and the same horizontal asymptote. This graph is supposed to cross the y-axis at 1/4. So it looks to me like B would not be an option. This looks higher than 1/4. It looks to me like this one's out of the running. But the last thing we would use to confirm is this table of values they asked us to just complete. At x equals -7, I should be at a very, very small negative fraction. There should be a point at -7, -1/45. And if I look at this graph, it does kind of look like that would be appropriate. This one, it looks like the function is above the x-axis there, so I do not believe that the C is the correct choice. So therefore, just based on that one table value, it looks like A is correct. So that's an impressive amount of work, but it's kind of a nice summary of several different topics that we've looked at.